So exam 2 is on Monday. That's October 9th. And the topics will be everything up through 2D kinematics. There's one problem on there, just problem 1, that might be a little confusing right now, but hopefully the stuff I'm going to talk about at the start of this class will make more sense. Everything else you can work on now. So after today, you can work on all these. Remember that it's cumulative, so you should go back and look at the old assignments. And I think one nice way to review those old problems is to look at it and just sort of ask yourself, the steps to take to do it, And if it jumps right to your mind, then you're probably good on that. Move on to the next one. Okay. And then the next thing before I get into new stuff, does anyone have any homework questions? Okay. So the last thing I want to talk about with 2D kinematics is an intuitive understanding of acceleration in 2D. Acceleration is a hard thing to wrap your head around. Most of the time, if you think that you have an intuitive understanding of what's going on, outside of like the kind of stuff that like this that I'm going to tell you, there's a good chance you're confusing it with velocity. Velocity is really easy to picture intuitively, and so a lot of times you'll start mixing up acceleration and velocity just so you can understand it. And then you're not understanding it, but you feel like you are. So anyways, you have to be careful thinking about acceleration. So in 1D and 2D and 3D, acceleration is a change in velocity. Well, I shouldn't say is, but it represents a change in velocity. It's not exactly the same thing, but it's related to it. So if velocity doesn't change, acceleration is 0. You can think of constant velocity and 0 acceleration as being synonyms. They mean the same thing. So if velocity doesn't change, acceleration is 0. That's true in 1D where velocity and acceleration are just numbers, and it's true in 2D where they're vectors. So that's true in either case. But here's where things are different between 1D and 2D. If velocity does change, then in 1D, let's do that first. The only thing acceleration can do is change the speed. It can only make an object speed up or slow down. There's a new way that velocity can change in 2D, though, that doesn't exist in 1D. So in 2D, acceleration can, first of all, it can make objects speed up and slow down. But it can also make objects turn. And the total acceleration vector comes from, there's a part of the, so for any acceleration vector, there's part of the acceleration vector that's making the thing speed up or slow down. And part of that acceleration vector is making it turn. And those two parts they're each vectors, and you add those two vectors together and they give you the total acceleration. So I'm going to give you a way to sort of visualize this. So to visualize the acceleration vector in 2D, first, draw the object's path. And I'll do an example, probably two examples. So draw the object's path so you can see what road it's following as it travels. Second, draw the velocity vector tangent to the path in the direction of motion. Now, third, if the object's speeding up, draw a vector that I'm going to call A parallel. Okay, so because it's parallel to the velocity vector, in the same direction as the velocity vector. If, on the other hand, the object's slowing down, draw that vector A parallel in the opposite direction of the velocity vector. Okay, so that's part of the acceleration that makes the thing speed up or slow down. And then last, draw A perpendicular well, first it's perpendicular to the velocity vector. in the direction the object's turning. And then the final idea is that the total acceleration vector is just the sum of those two, a parallel and a perpendicular. Okay, so hopefully this will make more sense after I do a couple examples. So let's say there's a ball rolling down a ramp. First, let's just say it's a flat ramp. And the ball's rolling down under the influence of gravity. Okay. So the object's path looks like this. What direction is the velocity vector? It's in the direction the object's traveling, so it's parallel to this path in the direction that it's moving. So I'll draw it like that. There's the velocity vector. If this object's rolling down the hill, would it be speeding up or slowing down? Speeding up. So the part of the acceleration that's parallel to v, is it in the same direction or the opposite direction? Same. So I'm going to draw a parallel like that. Is it turning? No, the thing's rolling over, but it's a particle, so we don't care about its orientation. It's not, its line isn't changing. And so a perpendicular is 0. And so the total acceleration is equal to this plus 0. So it's in this direction.
So if it was turning, what would, like, how would you?
Okay, so I'll do an example like that. Okay, and notice that this was something you did on the lab exam. When we thought of this as just a one-dimensional motion, there was a ball going up or down a ramp, and you had to draw the direction of the velocity and draw the direction of the acceleration. Right? The thing wasn't turning, so that's all there was to it. Okay, so now let's say instead of rolling down a straight ramp, this ball's rolling down something like this. Okay, so the path it's going to follow is going to be like this. So at this point, we have to figure out what a tangent to that path looks like. So it would look something like that. At this instant, that's the velocity vector. If this is rolling down the hill under the influence of gravity, would it be slowing down or speeding up? Speeding up. And so the parallel part of the acceleration is in the same direction as that. Okay, so green is the parallel part of the acceleration. And now in this one, we have to think about which way it's turning. Like if you imagine, there's a couple ways you can think about this. One is you can imagine that any curve is part of a circle, and the direction it's turning is towards the center of the circle. So like if you fit a circle to this thing, the center of the circle is that way. Okay, so that's the direction it's turning. You could also think about like that we're looking at a top-down view of somebody in a vehicle. Like imagine a driver here. And for this driver to stay on this path, would the driver have to turn left or turn right? You know what I mean? He'd have to turn left, you know. And so the direction this is turning is that way. It's perpendicular to the velocity in the parallel part of the acceleration. It's either that way or that way. And in this case, it's that way. Anybody have any questions about that, or does that make pretty good sense?
Would it always be like a 90-degree angle?
It's 90 degrees.
Because you said it's...
Yes.
Okay.
So that's why, yeah, one of these is parallel to the velocity,
Yeah.
and one's perpendicular to the velocity, always.
Okay.
So they're always perpendicular to each other. So for this thing to stay on its path, the perpendicular part of the velocity vector is this. And so the total acceleration vector is this plus good enough. This. And so to add those, you put them head to tail. Let me, I'll keep the same colors. So that one plus that one gives you a total acceleration like that. Okay, so that's the basic idea, but there's one more thing we have to consider, and that's that thinking about it in this way, there isn't any way to know what the relative lengths are of A parallel and A perpendicular. Okay, we know that they're in those directions, but we don't know the magnitudes. So remember doing this in lab last week, where we're adding two vectors where we know the directions, but we don't know the magnitudes. So the last thing is we know the directions of A parallel and A perpendicular, but not the magnitudes. And so that means that there's a range of possible directions for the acceleration. And the range of acceleration vector directions is from this, that was A perpendicular, to this, that was A parallel, and anything in between. So the acceleration could be anything in this quadrant. It can't be anything outside of that. Okay, let's do another one. So let's say it's the same kind of ramp thing, but this time under the influence of gravity, the ball's rolling up the ramp. Okay, so first we have to draw the path that the ball follows. That's like that. Then we have to draw a velocity vector, and it has to be tangent to that path. So at this point, it would look like that. Then we have to think about whether this object's speeding up or slowing down. Which one would it be doing here? Slowing down because it's going up. So the parallel part of the acceleration is opposite this. And now for the perpendicular part, yes? Nope, this is all true no matter what the coordinate system is. So the coordinate system would tell you, would determine how these vectors would be represented as components, you know? But that's all the coordinate system would do here. These vectors are what they are, independent of the coordinate system. So they're just directions. And so now we have to think about which way this is turning. There's two possibilities. The two directions that are perpendicular to this line. One's that way and one's that way. So which one is it? Towards the center or through the... Yeah, right. It's like if you think of fitting a circle to this, it's towards the center of that circle. So the perpendicular part of the acceleration is like that. And then the total acceleration is this plus this. So something like that. And if you consider all of the possibilities for the directions, it would be everything between this and this. So if you get in the habit of thinking through these steps, you can look at a picture like this and get a sense, an intuitive sense of what direction the acceleration is going to be. Okay, and you can't get it exactly, but you can get it within 90 degrees. Okay, so we did, the first example was one where the thing wasn't turning, it was only changing speeds. Then we did two where it was doing both. So let's do one where it's only turning, but the speed is constant. Okay, so let's think of like a tether ball. So this would be a top view, a view from up above. So here's the pole, and the ball's like this, and it's moving in a circle around the pole. We have to choose a direction. Let's say it's going this way. Okay, so this ball can be swinging around at a constant speed. That black circle is the path that the ball would travel. And it's going around that path this way. So the first thing we have to do is draw the velocity vector tangent to the path. So that would be like this. Next, we have to draw the parallel part. Well, this isn't speeding up or slowing down, so there's no part of the acceleration that's parallel. Okay, and then we have to think which way it's turning. So, is it turning this way or this way? Yeah, toward the center of that circle. So the perpendicular part of the acceleration is like that. And so in this case, the total acceleration is equal to something in this direction plus 0, which just has to give you something in that direction. Question? Yeah. How did I know it was going toward the center instead of out? It's always so when something's turning, there's always like a concave side and a convex side. You know what I mean? There's a side that's like so any curved shape has a side that would hold water and a side that the water would drip down. You know what I mean? Okay, so here's the side like the inside of a spoon that would hold water. Okay, the outside would not. Does that sort of make sense? It always points towards the side that would hold water. It always points towards the concave side. Yeah, that made it worse. What? Okay, so think about the path. Okay, the path that it's traveling. So one way is like imagine a driver here. Like imagine a driver that's facing the way that it's going. Okay, does that driver have to turn left or turn? And imagine that driver is the only thing keeping it on the path. Okay, does that driver have to turn left or right to stay on that path? Left. And so if he's going like this, then a perpendicular is to the right. To the left. Yeah, that was the worst time to.
And you know it's constant speed
because I said that in the problem.
Oh, okay.
Yeah, so I just gave you that. Yeah.
Because I said so.
Right. Yes, that's right.
So,
yeah.
Sorry, if you were to give us a problem like this, would we be required to draw it out, or would it be drawn for us, or how would that appear?
So I would draw something like the shape of the ramp or whatever, and you would have to draw the path that the thing's going to follow, and then draw the velocity, the two parts of the acceleration, and then show what acceleration directions are possible.
Okay.
And we're gonna, I think it's the next lab, but it might be 2 labs from now. We're gonna spend the whole time doing this.
Oh,
And so, it'll make a lot more sense after you've practiced it some. But we're just gonna try to drill this approach into your head so that it's sort of natural to go through these steps. But one more thing that's gonna be, when we eventually talk about circular motion, one thing that this shows really clearly is that if something's moving in circular motion with a constant speed, the acceleration, no matter where the thing is on the circle, is toward the center of the circle. And we can see why by thinking about it this way. Any other questions about that right now? So like I said, that's mostly just something we're going to do in lab, and it's going to be on lab exams and stuff like that. But for number 1 on 2D kinematics, you have to think about it in this way a little bit to make sense out of that question. Okay. So that's the end of 2D kinematics. So now we're going on to 2D kinetics. Still particles. Okay, so we're making a distinction between kinematics and kinetics. Who remembers what kinematics is? That's right. Yep. So this is just describing motions, a motion description in terms of position, velocity, acceleration, time, without talking about the causes. So now we're going on to kinetics. And kinetics still includes all the kinematic stuff. But now we're going to talk about the causes of the motion. And those causes are force, mass, and a little later on, energy. But for now, we're just going to deal with force and mass. So the first thing we have to do is introduce these new terms, mass and force. I'm going to do mass first because it's easier. So mass is a measure of an object's resistance to acceleration. And you're most used to thinking about mass in terms of the weight of something, and it is related to the weight. So like if you so this is supposed to be a semi-truck. We don't talk like that here. This is America. This is like a Yugo. If these collide, the reason that it's really, really bad for the person inside the little car is that this truck has a lot of mass, and collision is not going to cause it to accelerate very much. The little car has very little mass compared to the truck, and so when they collide, it's going to accelerate a lot. And, you know, there's two things that are bad about car collisions. One is getting impaled on stuff. That's bad. But then the other one is just really, really big accelerations. And whoever the person in the car, you know, after this collision, the truck is going to keep moving in this direction at a speed not too much different than what it was going before the collision. The car is going to go from its full speed that way, you know, its full velocity this way, to an entirely opposite velocity in a very short amount of time. And so that acceleration is going to be really big, and it's going to, you know, wreck a lot of parts of bodies. And so that's the relationship between the weight that you would measure on a scale or whatever, and an object's inherent resistance to being accelerated. The heavier something is, the less it's accelerated by the same impulse. That's why coaches want big football players, because you want people who, when they get into these collisions, have an inherent resistance to being accelerated. And so if a 150-pound person gets in a collision with a 300-pound person, all things being equal, you know, there's a lot of variables that come into it. But the 300-pound person is going to keep moving close to the velocity they had before the collision. The 150-pound person, their velocity is going to change really quickly, and that acceleration is going to be big. Any questions about that? So one thing to notice about mass is mass is always a positive number. And because of that, it doesn't have any direction. There's no such thing as somebody having a mass of 100 kilograms facing west, but only 50 kilograms facing north or something. You know, it's a property that's independent of orientation. And the units, the SI units for mass are kilograms. And that seems a little weird, I think, maybe if you think about it, because you think of adding these prefixes to sort of the more fundamental things. So you'd think maybe the standard unit would be grams, and kilograms, you know, is adding on to that, but that's how it is, kilograms. Okay. And the other new quantity that we have to talk about is force. And force is a measure the direction and intensity of push or pull on an object. Since it includes direction, it's a vector. And the units of force always have a unit of mass times a unit of acceleration. And the SI units, well, the units of mass in SI units are kilograms. What are the units for acceleration? Meters per second squared. And so the units of force are, SI units for force are kilogram meter per second squared. Force is something we use all the time, and that's a pretty cumbersome unit to carry around all the time. And so 1 kilogram meter per second squared is given the name Newton. And the abbreviation is capital N. Okay, so now how can you figure out all the things that are pushing or pulling on an object? You know, all the pushing or pulling. What? Different things. Yes, I suppose you can. We'll, we're not going to have to deal with that. But I guess what you would do in that case, if it was really like one thing causing both of them, you just deal with, one's going one way, one's going the other way, you'd add those two vectors up and just take what the vector added to. You know, like if you pushed in one spot on an object with 100 newtons at the same time you were pulling on it with 100 newtons, that's just zero force, and that's what we'd call it. So how can you figure out all the things pushing or pulling on an object? That sometimes feels like a little overwhelming at the start of a complicated problem, but this is an important thing to keep in mind, and I'm going to try to keep emphasizing this. In this class, there are only two types of forces. Only two ways forces can be applied. The first one is by gravity. That's the weight. And the second thing is contact with a touching body. So if you're trying to figure out all the forces acting on a thing, so let's say all the forces acting on this, whatever it is, there's a weight force pulling down on it, and now you're just looking for all the things that are touching its boundary. In this case, the only thing touching the boundary is the desk, so there are only two forces acting: weight pulling down and a desk force, which happens to be pushing up. I'll talk about how we know that later. And so, yeah, that's a useful way to sort of simplify problems that look complicated at first. I want to say one thing too about so the force that's applied by gravity is called weight. Okay, but like your bathroom scale, mine anyways, has a switch on the bottom where I can choose whether to have it in pounds or in kilograms. And kilograms is a measure of mass. And I'm making a distinction here between force, which has units of newtons and it's a vector and all this stuff, and mass, which has units of kilograms. It's not a vector. They're totally different things. So how is it that your bathroom scale has a conversion between units of force, pounds, and a unit of mass, kilograms? And the answer is that your bathroom scale really measures the force that you're applying to it. That's all that's what it does. It can't truly measure mass. But the clever people at the bathroom scale manufacturing plant know that you're probably using that bathroom scale somewhere near Earth sea level, the surface of the Earth. They're assuming you're using it on the surface of the Earth. And so they know for a given amount of mass how hard gravity is going to pull on you. And so there's just a conversion based on, the fact that we're on Earth going from mass to weight. But if you used a bathroom scale on the moon, it would accurately tell you the force in pounds that you're applying to the scale, but it would give you a very inaccurate reading of your mass. Your mass on the moon is still the same, but because gravity doesn't pull as hard, you don't apply as much force to the scale. So if you ever want to quickly lose weight, I do this all the time. It works awesome. Take your bathroom scale somewhere with a little weaker gravity. The moon works awesome, but that's hard to get to. To the moon? Okay, well, apparently the biggest thing that affects the strength of gravity isn't the altitude, although that does have some effect. Apparently it mostly has to do with the geology around where you are, because big rock structures have more mass, and that mass is what's causing the gravitational pull. And so the altitude does affect it, but it's not the main thing affecting it. But if altitude was the main thing affecting it, okay, so if the Earth was totally uniform, there were no like big rock structures here and not over here, then there would, based on altitude, be a difference in the free fall acceleration at sea level compared to on top of a mountain. Okay, but the difference is really small. Like I think I remember at sea level, the acceleration of gravity is 9.80655. We call it 9.81. on the top of Mount Everest, the acceleration of gravity would be 9.804, I think. Like a tiny, tiny difference. So not much. But if you get, outside the atmosphere and whatever, then there are big differences. Any other questions right now? Okay. So we've been talking about vectors and how to express vectors as components. So in the vector discussion so far, you can calculate a vector's components in any coordinate system. What? That's you can calculate a vector's components in any coordinate system, and I did give a couple rules. They had to be x and y had to be perpendicular, and it had to be a rotated but not flipped version of one we're used to. Remember that? But I'll just say in any coordinate system. Now we're going to be more restrictive. So if we're talking about force vectors, we're going to need to be more restrictive. The coordinate system must be what's called inertial. Means for a coordinate system to be inertial is the origin can't be accelerating. And second, the axes can't be rotating. They can't be changing orientation. Okay, so there's those two requirements about what kind of coordinate systems we can use for kinetics. But if you have an inertial coordinate system, so if the coordinate system is inertial, you can think of the force vector being defined this way. So the force vector is defined by Newton's second law. I'm going to always abbreviate that N2L because we're going to talk about it all the time. And Newton's second law says the net force vector is equal to the mass times the acceleration vector. You might have heard of this equation before. And let me give some some sort of strict definitions of these things in this equation. F net is the sum of all force vectors acting on a chosen object M, bless you, M is the mass of the chosen object, and A is the acceleration vector of the chosen object. So this idea of being very clear about what object you're choosing, what's the chosen object for using Newton's second law is going to be really important. But this is, Newton's second law is the most important equation in this class. And in a group of 4 equations or something, that would be a candidate for the most important equation in all of physics. Yes?
So when you say origin can accelerate and
Okay, yeah. Well, okay, so that so you can always think of a coordinate system as like a video camera. That's a way to think about it. Like, you know how, like, if you have a good video camera and there were marks all over the room, so you could tell where things were at different times. You know, you could tell how many meters that way and how many meters that way. You could take all your kinematics measurements from a video. Like, could you imagine like a so, okay, yeah. So imagine a room that's all up the walls, along the floor. Everything is marked out 1 meter in meter increments all the way. And so wherever something is, you could tell how many meters it's moved in how long. Okay. And if you used a video camera, you could measure how the position's changing over time. And based on that, you could calculate the velocity as a function of time and the acceleration as a function of time. So you could get all those kinematic measurements from this video camera. Okay. If that video camera is not accelerating and not rotating, then the acceleration that you measured with that video camera would satisfy this equation compared to the forces that were being applied to things. But okay, so now think there's this room, but one wall's missing, and you're taking those same measurements, but you're taking them on a video camera that's accelerating past the room, like it's on a car that's speeding up or something. You could take the measurements the same way and calculate the accelerations and stuff the same way. But the accelerations that you measured would not satisfy that equation when you compared them to the forces applied to things. So that's about the best I can do, I think, to explain that. But basically, yeah, if you always think of a coordinate system as a video camera that's observing everything, that video camera can't be accelerating and it can't be turning. Any other questions right now? there is such a thing as Newton's first law. We'll talk about that in lab, but it's not going to be useful calculations because Newton's first law is actually implied by Newton's second law. So Newton's first law is the one that says an object, if no forces are applied to an object, or if all the forces add up to 0 on an object, it keeps moving in a straight line with a constant speed. That's Newton's first law. But Newton's second law tells you that's the case. So we're just going to stick with Newton's second law. And a big sort of take-home message here is notice it's very important to be clear about what your chosen object is. And this is the biggest reason why we're going to spend a lot of time doing these things called free body diagrams. So that's why free body diagrams are going to be important. Okay. Like I said, there are two kinds of forces that can be applied to objects in this class. There are some other ones that can be applied. We're just not going to deal with them, but it's not really too different to include them. But other forces that can be applied are forces applied by magnetic fields, forces applied by electric fields. We're just going to deal with gravity and contact forces. So the first type of force is the weight. And so we have to figure out how much force gravity applies to things. Well, we've already talked about how something in free fall, we know no matter what its mass is, it has a downward acceleration of 9.81 meters per second squared. So we're going to start with that. We know the acceleration in free fall is 9.81 meters per second squared down. Now let's first consider we're going to use Newton's second law and what we know about the acceleration of something in free fall to figure out what the force is that gravity applies to a 1 kilogram object in free fall. Okay, so force does gravity apply to a 1 kilogram object in free fall? The reason that I'm going to think first about something in free fall is because the definition of free fall is that the only force acting on an object is gravity. So we can just isolate what the force is that gravity applies. So if we choose a coordinate system like we normally do, where y is up, and Newton's second law says for a 1 kilogram object in free fall, the force vector, we're going to figure out what those components are, is equal to 1 kilogram. You know, the force acting on it is equal to the mass of the object times the acceleration of the object. And what's the acceleration vector of the object? Yep, 0 for x, negative 9.81 meters per second squared for y. And for these vector equations, we can do the x and y part of the equation separate. So we can think of this as two separate equations. The x equation says fx is equal to 1 kilogram times 0. So that's 0. And the y component of the force is equal to 1 kilogram times negative 9.81 meters per second squared, which is negative 9.81 kilogram meters per second squared, or negative 9.81. Okay, so what we found out is that the force of gravity, the weight, is 9.81 newtons down. Okay. So we've only thought about it for a 1 kilogram thing, but it would make things nice and simple if it just turned out that gravity pulled 9.81 newtons down on everything. And we could move on. Yes? Yeah, it's down because it's a negative y component, and we had already decided that the negative y was down. Okay, so now let's do another one. So say that's our working hypothesis, is that the weight pulls 9.81 newtons down on everything. So now let's think about 100 kilogram mass in free fall. First, be very careful with 100 kilogram masses in free fall. Okay, so Newton's second law here says Fx and Fy is equal to the mass times the acceleration. What's the acceleration of the 100 kilogram mass in free fall? Still the same. So 0, negative 9.81 meters per second squared. Solve this and you get Fx is 0. Now Fy is negative 981 newtons. So 981 newtons down. So what we see is that gravity pulls harder on the heavier thing than it did on the lighter thing. And so now, I mean, we could have just done this at the start, but I did those two with numbers just to sort of motivate this last one. What's the, so 3, let's say we just have a mass m in free fall. Then Newton's second law says the components of the weight force are equal to m times the acceleration in free fall and so Fx is 0 and Fy is negative 9.81 meters per second squared times m. So if you define 9.81 meters per second squared, you call that lowercase g, then the weight acts with a force vector mg down. Okay, so there's what gravity does. And so now I want to clarify something that's sort of confusing. Well, I don't think this will clarify it, but I want to keep trying to clarify this. So in short, gravity applies different forces to everything. To each thing according to their mass. So gravity pulls down with a higher force, with a bigger force on a car than it does on a book. Okay, gravity's applying different forces to things based on their mass. But in free fall, everything's acceleration is the same. Regardless of the mass. I think that's the difference between those two things is sort of confusing to people. Like, we've been spending all this time talking about how gravity in some way behaves the same no matter what the mass is for two objects. But now we find out it's pulling harder on the heavier thing and less on the... But it all just comes down to Newton's second law. And if you think about the fact that mass is something's resistance to acceleration, okay? Something with a big mass is very resistant to acceleration. Something with a small mass is really easy to accelerate. So gravity pulls harder on a car but it pulls exactly the amount harder on a car than it does on a book that's required to accelerate the car. The car is harder to accelerate. Okay? And so the accelerations end up being the same even though the forces are different. Yeah. Yes, if there's no air resistance, yes. If you dropped a car and for sure, if you dropped a car and a lead and a little lead ball, you know, off of a building, they would fall exactly the same. But the car would be, that whole time, the car would be being pulled harder by gravity. Okay, I guess that's all today. Anybody have any questions before stop?